Chapter 14, Section 2, Optimization. Now you understand how to train a neural network. Next, let's see how to optimize parameters in a deep learning model. Regardless of whether the problem is a regression or classification, we need to evaluate the model's prediction performance to find the best model. Based on the performance evaluation, the neural network adjusts the parameters to improve the model performance. The prediction performance of a neural network is evaluated using the loss function. Loss function quantifies the degree to which the model's predicted values are deviated from the true values. The smaller the loss function's returned value is, the better the model performance is. We train the neural network to make it learn the parameters that minimize the returned value of the loss function. There are various types of loss functions. Let me introduce common loss functions. When we apply a neural network model for a regression problem, we can use mean squared error or mean absolute error as loss functions. For classification problems, we can use cross-entropy loss. Mean squared error, usually called MSE, is the most popular loss function used to evaluate a regression model's performance. It is the average of the difference between the true values and model's predicted values. One of its strengths is that it can penalize a large amount of error. A weakness of MSE is that it is susceptible to outliers because it is the sum of squared values. Mean absolute error, usually called MAE, is another loss function that is commonly used to evaluate a regression model. Compared to MSE, MAE is less susceptible to outliers because it is the sum of the absolute error, that is, the absolute value of the difference between the true values and the predicted values. So, MAE is more appropriate than MSE when the data contains outliers. Cross-entropy loss is a common loss function to evaluate the performance of a classification model. It quantifies the difference between the predicted probability distribution and the true probability distribution. By the way, why do we need to compute the loss function? For example, as the classification problem, why don't we use the accuracy rate, that is, the proportion of correctly predicted cases to the total cases? It can be computed more easily than a cross-entropy loss. The reason is that a neural network uses differential to learn the best parameters. As we know, a neural network is trained to learn the parameters that minimize the returned value of the loss function. That is, a neural network tries minimize the loss function by changing the parameters slightly and observing the associated infinitesimal differences in the loss function. So, a neural network uses differential to learn parameters. The advantage of using a loss function is that the differential of a loss function will never be zero. So, a neural network can continue to learn until it finds the best parameters. On the other hand, the differential of the parameters will be zero in most cases. This explanation relates to the gradient method, that is a commonly used method for a neural network to learn parameters. Differential can be expressed by this formula. Let me briefly explain what is expressed by this formula. Differential can be used to identify the gradient of a function. Differential sees a variable's infinitesimal change and the associated change in another variable included in the function. Let's look at this curve. This curve depicts combinations of x and y in a function. There are 2 points whose x-coordinates are small x and small x plus h, respectively. Suppose the x value changes from x to x plus h, so the x value changes by h. It is a move from the green point to the orange point. Let's write in a straight line that connects the 2 points. The straight line is upward sloping, meaning that the y value increases as the coordinate moves from the green point to the orange point. In other words, the upward sloping line shows that, in this function, as x increases from x to x plus h, the y value increases. Since differential sees a variable's infinitesimal change, let's bring h as close to 0 as possible. In this case, the line that connects these 2 points is almost the same as the tangent line at these points. As we can see, the gradient of the tangent line is upward, meaning that, in this function, as the x value's infinitesimal change from x to x plus h, the y value increases. Let's go back to the formula. If we plug in x and x plus h values in this formula, and we get a positive value, it means that the gradient of the tangent line is upward. If we get a negative value, it means that the gradient of the tangent line is downward. Gradient descent is an optimization algorithm that identifies a local minimum of a differentiable function. More simply put, gradient descent finds the minimum value based on the gradient of a function. Let's look at the graph of a simple function. Using this example, let's identify the x value that minimizes the y value. Suppose we are here. At this point, the graph is downward to the right. It means that y will be smaller if we go to the right. So, let's go down to the right along the line of the graph. The y value got smaller, but the graph is still downward to the right. Let's go to the right. Now, at this point, the graph is downward to the left. We moved too much. The y value will be smaller if we go to the left. Let's go to the left a little bit. Here, the gradient is 0. It means that y is the smallest at this x value. This is the optimal x value that minimizes y value. This is a simplified example, but when we train a neural network, we use differential to find the optimal x that minimizes y. That is, by using a gradient descent, we can find the optimal parameter value that minimizes the loss. Usually, we use mini-batch learning to optimize the parameters. That is, we apply mini-batch gradient descent for parameter optimization. Suppose we have a training dataset consisting of 1,000 cases. In mini-batch training, we did not use all 1,000 cases for one-time training at once. Instead, we use a smaller number of cases, for example, 200, as a unit for one-time training. In this case, we select 200 cases randomly from the 1,000 cases, and use the 200 cases as a learning unit. Then, when the learning is completed, select 200 cases randomly again, and use them as a learning unit. And repeat the process. This is the process of mini-batch learning. The number of cases randomly selected for one-time learning is called batch size. So, in this simplified example, the batch size is 200. Here, we have 1000 cases and set the batch size to 200. So, probabilistically, by repeating the process of mini-batch learning 5 times, we can use all cases in the training set. In this case, this 5 times repetition to complete using the whole dataset can be regarded as a unit called epoch. In real cases, the epoch is repeated multiple times. The number of epochs represent the number of these repetitions. So, in this simplified example, the number of epoch is 3. Actually, we set aside 20 to 30% of the training data as a validation dataset. A validation dataset is similar to test set in that it is used to evaluate the performance of models developed using the training set. But it is different from a test dataset in that while a test dataset is used in the phase of model testing, a validation dataset is used during the model training to check the progress of model learning. By taking the number of epochs on the horizontal axis and the output value of loss function on the vertical axis, we can depict a figure that represents the model's learning progress. Thank you for watching. Please thumbs up and subscribe to my channel.